Hello guys, I'm back. In this video, I will teach you how to do the calculations for the pipe wall or pipe thickness based on Asme B31.3 process piping. My name is Jeferson Costa and I teach students, graduates and engineers how to work with chemical process engineering and plant design. And just before I start, let me tell you a secret. I will use two PDF files here as reference for this class, and I will let them available in my Telegram channel in process once this video reach 100 likes. So if you want to get those two PDFs that I will use in this class, give your like right now. One of the activities of a chemical process engineer working with plant design is to deal with pipe sizing for transportation of fluids. And to be able to do that, we need to have the initial heat and material balance of the system, or at least the requirements of the fluid that must be transported. So based on that, I will share with you here an example where we have water, and based on the process conditions, we'll do the preliminary pipe sizing of the system. So in this case, my requirements for operating pressure is 2.5 bar G, and as I dealing with cooling water, my cooling water needs to have 28 Celsius degree, and my flow is for references in this case will be 65 cubic meters per hour. With this initial information, the chemical process engineer can start in doing the preliminary pipe sizing. That depends on the sizing criteria used in the project. Sizing criteria can be based on the pressure drop per length and can be based on the velocity of the fluid and other criteria. Here, as I don't have the plot plan of my system, of my process, I will use the velocity criteria. And considering that I am getting the pipe sizing at the discharge of a pump, I will use a sizing criteria 2.5 meters per second. So to do the preliminary pipe sizing of a system, we need to define, or we need to calculate the initial pipe diameter. And to calculate the pipe diameter, we have here three equations. In fact, for pipe diameter, I have that it is 4 times the flow rate divided by P number multiplied by velocity and the square root of this calculation. So if I rearrange this equation, I can get the velocity and I can get the flow rate. Something to observe is that you need to have consistent units of measurement. In most of the cases, the flow of fluid, the volumetric flow of your system will be measured in cubic meters per hour. So to use the equation 1, I need to convert that to cubic meters per second, because my velocity reference for my velocity is meters per second. So when I do that, the yellow highlights are numbers that I set to my system, and the other ones are calculated. So you can see here that the internal diameter and the calculations for the velocity is based on the internal diameter, but the pipe sizing selection is based on the outside diameter, or nominal pipe size. So in this way, when I do the calculations, I get my internal diameter as 96 millimeters. So this is the references for my internal diameter. And to do the pipe wall thickness calculations, I need to go to Asme B31.3, and in the section 304, Threshold Design of Components, I find that for a straight pipe, my wall thickness will be the calculation of the wall thickness for internal pressure plus allowance for corrosion, erosion, and etc. So based on that, I have the following equation where I have that the thickness of wall thickness is based on the pressure multiplied by the pipe diameter. in this case the outside diameter or nominal pipe size, divided by 2 times the stress value for material multiplied by the quality factor multiplied by the weld joint strength reduction factor plus pressure multiplied by coefficient from table 304. So with those information, I am able to find the wall thickness, and with addition of corrosion allowance and erosion allowance and others consideration that I may have, I will get the total thickness or the minimal required thickness for my pipe size. So to start with, as the Asme B31.3 is an American standard, we need to use the units of measurement that fits to the code. So you can see that in my process data, I have bar G, Celsius degree, cubic meters per hour, but in my pipe wall tab calculation, I converted the pressure for PSIG because it's the pressure required for calculations, internal design gauge pressure, and here I am using the operating pressure, and I have the operating temperature. The second part to be defined is the material of my pipe. So as I using a pipe that is for water transportation, cooling water transportation, I defined my material as ASTM 106 grade B. So this is to let our life easier. Depending on the fluid that is being handling, the material needs may be different. But in this case, it was defined as the ASTM 106. So it's important to verify that this material has grade A, B, and C, and here I'm using the grade B. So the first thing to define to be able to use the equation is to have the pressure. So the pressure is already available, and we need to have the diameter of the pipe. So the diameter of the pipe I will get from my previous calculation, but remember that this calculation is related to the internal diameter. So I need to find a pipe size that matches or that is very close or around the inside diameter that I have calculated. And to do that, we can use some industry charts. So in this chart, I can see the pipe dimensions in weight available in commercial and nuclear based on information in inches and also in millimeters. Here I find the outside diameter, the schedule designation, wall thickness, weight, and internal diameter. So in my calculations, I have an internal diameter of 96 millimeters. So if I navigate in this chart, I am able to find what matches or is close to my calculations. I have here that the number near to my calculation is a nominal pipe size of 90 millimeters or 3.5 inches. But 3.5 inches is not a usual commercial pipe size. So instead of using 3.5, I will use a pipe size, nominal pipe size of 4 inches. And it is 4 inches or 100 millimeters. So when I return to my spreadsheet, here in the diameter, I will add the information of 4 diameter. And now I need to navigate in the code in the Asme B31.3 and find or use some tables that are available in the standard. So the first table that I will use is table A-1A or table A-1B. So based on that, I will look for the material that I using in the exercise or in this example. So I will need to look for ASTM 106 grade B. So I don't have that in my table A-1A, but I have that in my table B31.3-1B. I can find that for A106 it is a seamless pipe, so there is no welding to produce this pipe. I have that the basic quality factor is 1. So I will return to my paper wall tab, and on E I will add 1. So the next step is to verify the table A-1, because on this table I will find the basic allowable stress in tension for metals. So if I look for my table, I will verify that ASTM A106 grade B has a basic allowable stress, letter S, kilos of SI as 20. So I need to verify what is my temperature conditions. If I go to my process verifications, I have the temperature condition of 82.4 Fahrenheit. So based on that, I can look for, or I can use my minimum temperature to 100 Fahrenheit, because 100 is above my operating temperature. If I was operating at 150 Fahrenheit, instead of using the column for 100 Fahrenheit, I would use the column for 200 Fahrenheit. So based on that, I can see that my allowable stress is 20 kilo SI. So when I return to my calculations, I will identify here, or I will add the value of 20. And now I need to find the value for W. So W, I will go to the tab, or to the table 302.3.5, that in fact report me to the table 302.3.4. In the 302.3.5, letter A, it says that if I am using a seamless steel pipeline, my welding or my weld joint strength reduction will be 1. So in this case, my W will be 1. And now I need to look for the coefficient from table 304-.1.1. So when I go there, I will verify what is the material that I am using. So the ASTM 106 grade B is a ferritic steel, and I need to verify what is the temperature that I am considering. So my temperature is below 900 Fahrenheit. So based on that, my value for Y will be 0.4. So I return to my calculations and I add 0.4. And with that, I have the calculations of the thickness for a straight pipe under internal pressure. And you can see that the thickness, only because of the process conditions, the material conditions, is 0.004 inches. But as I adding a corrosion allowance of 3 millimeters, I am adding 0.12 inches to my thickness, resulting in a value of 3.14 millimeters as minimal required thickness for this pipe. And now that I have the 100 millimeters nominal pipe size, or 4 inches nominal pipe size, I will look for what is the wall thickness that will represent the schedule of my pipe. So based on that, I need to return to the chart with the considerations for the pipe size. So considering that what I need in terms of wall thickness is 3.14, if I look for the column that where I have this information, I have this column here with information in millimeters. So I need a wall thickness of 3.14 as a minimum. So when I return to my nominal pipe size of 4 inches, I will verify that I can reach the minimal requirements with 3.96 millimeter. I cannot use the wall thickness of 3.05 nor 2.11. My minimal wall thickness will be 3.96. So I will add that information for my spreadsheet. So here I have a 10S schedule for my pipeline that refers to 3.96 or 0.156 inches. So when I do the conversion, I have the same values of my table. And to finish the calculations, now I need to find what is the internal diameter, considering that I have a tube with 4 inches and I schedule 10S. So based on that, I can get this information straight from the chart. So here, for this line here, I have that the internal diameter is 106.38 millimeters. So this is the internal diameter size. So when I get this information, I will return this information for my spreadsheet. So 106.38. Now I do the calculation to verify if the conditions that I am considering make sense or not for my project. So you can verify that the new velocity is 2.03 meters per second because I have an internal diameter higher or bigger than the process data that I have calculated preliminary, and that my pressure, considering that instead of having 0.004 inches, I have 0.12 inches, my pressure verification can reach up to 111 bar G. This calculation is only for reference because besides the wall calculation of the pipe, a pipe system depends on the flange pressure ratio. So this is not the design condition for our process. It is just a verification to verify if the pressure allowed, considering this pipe wall thickness, matches with the requirements of the process. So I can see here that the requirement of my process is well below the calculated pressure of the system. So here at the first site, we could imagine or we could consider that for this system, I would use a 4-inch pipe size with a 10S schedule. And based on that, add this information for my pipe instrumentation diagram and let the pipe engineer or the pipe designer deal with the isometrics. But in real life, it is not the way that happens because we need to consider, or the pipe designer will consider a lot of other information. For instance, depending on how thick is the pipe size, they will deal with support for this pipe. There will be flatting. So it's not only a matter of the minimal requirements for the process. It deals the definition of the wall thickness or the pipe wall thickness also get into consideration how easy is to build and to erect and to install the pipelines in the field, in the process. So normally what happens when we are dealing with pipe sizing in a design company or in a design department is that we use the pipe specification manual from the company. For instance, here you can see a pipe spec for Petrobras. It is an oil company here in Brazil, where I have based on the service of my stream, in this case cooling water, I choose standard material AB, and this standard material will tell to me what is the kind of pipe material, in this case carbon steel, what is the maximum temperature that I can operate, the minimal temperature that I can operate, the corrosion allowed for the system, and what is the pressure rating for the flanges. So this kind of pipe specification is very common in the industry. Each company has its own. So based on that, if I am doing a project for Petrobras, instead of doing all of that calculations, what I will do? I will verify what is my flow that I handling. It is cooling water. So what is the temperature? What is the pressure? My temperature is 38 28 Celsius degree, so it is in this range. My pressure is 2.5 bar G, so I will verify in the chart if these material are able to handle that or not. So for this material, I can my design temperature, my design pressure is around 10 bar G. So based on that, as I operate at 2.5 bar G, these material are able to fit or fits to my process. So what I will do in terms of tubes, here I have tubes. My tube calculation, preliminary tube calculation was 4 inches. So between 3 inches and 6 inches. In fact, instead of using a schedule 10S to my process, I will need to use a schedule 40. So with this information, I can return it to my calculations and verify if I'm still getting the sizing criteria. So if I return it to the chart, I will verify that the schedule 40 in fact has an internal diameter of 102.26 millimeters, has a wall thickness of 6.02 or 0.237 inches. So let's update those information in the spreadsheet. With information updated, as I increase the schedule, my internal diameter gets smaller, and as expected, my velocity increases. But however, I have increased the velocity, it is still in the sizing criteria that I have defined in the preliminary calculations. So guys, with this, you have seen how to do the calculations for the pipe wall thickness based on Asme B31.3, and you have seen, most important, how is the procedure when we are dealing or when we are working in the industry. The calculations for the pipe wall most often is not performed by the chemical process engineer. It is done by the mechanical engineer, and it is very important to build or to develop the pipe spec that in fact will be the documentation used by the chemical process engineer. But in any case, if you are in a project that you don't have a pipe spec available to you, now you have a reference how to deal with things related to chemical process engineering and design. If you want to have those PDF shown during this class, just give your like, and once we get 100 likes, I will let it available in my Telegram channel in process. So guys, this is it. I hope you like it, and I'll see you soon in the next video. Bye bye.